Cool, thank you. Okay, thank you for the invitation to move up 3 floors. As Simon said, I'm a particle theorist, so I kind of ended up thinking about cosmology and astrophysics via that route. So there are some things that I know much, much less about than any of you do. And by the way, help is appreciated. So there are various calls for help in these slides. And anyone who wants to help out, please talk to us after. But I think it's actually really fascinating that in this day and age, there is such an active interface between very, very fundamental questions and literally astronomical observations of stars and X-ray sources and so forth, okay? So let me talk about the cosmology and astrophysics of the twin Higgs. So the particle physicist introduction, and I mean, I'm going to admit this is the same talk that I would give to a particle physics audience, but I think because it's mostly about cosmology and astrophysics, it actually works either way. As a particle physicist, I care about fundamental mysteries of the standard model, things like the hierarchy. Why is it vibrating? Things like the hierarchy problem, which is essentially why is the mass of the Higgs boson unstable with respect to quantum corrections, which is empirically speaking not strictly a problem, but incredibly weird if you don't believe in 1 in 10 billion tunings. What's dark matter? Where do the standard model baryons come from? Where does neutrino masses come from? So there's a bit of pessimism within certain aspects of the high energy community because the LHC has not solved all of these things when it turned on. But I don't really see this pessimism because the kind of models that particle physicists usually write down to solve these problems, things like minimal supersymmetry or minimal WIMPs, generally involve IR minimal spectra. So as few particles as possible at low energies. They have to have sizable couplings to do whatever they're supposed to be doing. And that gives rise to fairly minimal signature spaces that are hard to miss. Yeah, and then if you don't see them, you get sad. Now, these things haven't shown up, but it turns out that there's this much more broad class of signatures, which I think, if you guys work in cosmology, is familiar to you, are essentially hidden sectors. So particles or fields or forces that are hidden from us, not because they're very heavy or hard to produce, sort of in terms of the amount of energy you have to put in, but they just don't couple to us all that much. And dark matter is one of those things. Dark matter is not difficult to come by. There's plenty of it. We just don't know how to couple to it. A sort of going back in time a little bit, in modern language, neutrinos were a hidden sector back when they were proposed, right? So now we understand, so a sort of cartoon of hidden sectors is here is your spectrum of states in the standard model. And then there are some states in some hidden sector with no kind of direct coupling, like no electromagnetic coupling or whatever. But there could be, for example, a heavy mediator particle you can excite to go down, or a very small coupling via the Higgs, or a small coupling via the photon mixing. And if you somehow land in this hidden sector, then you have to climb through these tiny portals back to the standard model to be detected. So by that logic, the Z boson is the heavy mediator that gives access to the neutrinos, or the W boson, which are the hidden sector of neutrinos. Yeah? So now we don't talk about it that way because we have the standard model as a complete structure. But historically, this is not weird. Yeah? So maybe the next layer of the hidden stuff is dark matter or other things. So this is worth investigating on very general grounds. As a particle physicist, there are 3 important lessons that we draw from this. The first one is that the Higgs boson, this recently discovered particle, is an exquisite probe of these new fields. Because the Higgs, by its nature, the very same lack of quantum mechanical symmetry protection that makes the Higgs vulnerable to quantum corrections from all scales, and that's the hierarchy problem, that same lack of symmetry means it's vulnerable to coupling to anything that exists. So the Higgs portal generically means the discovered Higgs that we found will couple to whatever you put out there. And the Higgs is a very fragile little creature. Its decays are governed in the standard model by very small couplings. So if it decays to other things with also very small couplings, those couplings will not be small in relation to what's already there. So it could give rise to detectable deviations. So the Higgs is a very sensitive probe of new physics. Similarly, hidden sectors generally give rise to metastable states. That's not hard to understand. You have small effective couplings. Metastable states in particle physics show up as long-lived particles. Now, to particle physicists, long-lived is anything that travels for more than, say, 0.1 millimeters. Now, that's enormous on subatomic size scales. For cosmologists, long lifetime means something different. But even you guys, like more than a second is going to mess with BBN, and we don't like that. Yeah. So long lifetime is above atomic scales, but the lifetime itself is almost a free parameter just because it varies so strongly with various inputs. And finally, kind of the moral heart of this talk is that there's a very strong complementarity between cosmology and colliders. So if you have a hidden sectors, if you think of the standard model as a sort of interacting system of fields, electromagnetism, nuclear forces, right? Everything is in this well, sort of metaphorically. The hidden sector is another system of things, but if I have a small coupling between them at low energies, like these photon portals, Higgs portals, etc., I'm going to have metastable states in the hidden sector decaying to the standard model, and that I can see at various colliders like ATLAS or CMS. And some of you might be aware, I'm working quite a bit on an experimental proposal, which is a little bit intimidating as a theorist, called Methuselah, which aims to detect these very, very long lifetimes that escape the detector. Yeah? So I'm not going to talk too much about that here, but that is sort of one lever arm of this world of theories. And we need very good detectors at the LHC to find these things. But if these are two bathtubs and a little drain in between them, I can cut that drain. And in symmetry language, I'm making the hidden sector absolutely stable. And now we're in your playing field. I have non-standard cosmological relics. I have dark radiation. I have these things that will modify structure growth, all this kind of stuff. And that's what I want to talk about in this talk. Yeah? And what's really interesting is that the kinds of models that particle physicists talk about as giving these long-lived particle signatures, these kinds of models are fundamentally motivated. They can solve the hierarchy problem. They can solve baryogenesis, all that kind of stuff. And they will point towards very specific non-standard cosmologies in astrophysics. So, and I think this is a very important approach to think about non-minimal dark sectors, because in general it's true, we don't know what dark matter is. We're pretty complicated. Maybe dark matter is complicated too. That's absolutely true, but doesn't really get you anywhere. Yeah? If you have some kind of UV mystery, some kind of fundamental reason why a particular family of dark sectors makes sense or not, I'm not saying that's the dark sector, but it's at least a starting point to start exploring the signature space, both cosmologically and astrophysically, of what would otherwise be an impossibly complicated signature space of arbitrarily complicated dark sectors. So if you have the hierarchy problem pointing you towards certain theories, maybe start there. Yeah? So that's the particle physicist's way of starting to get into these nitty-gritty cosmology pieces. And to me, well, then you generalize a little bit. To me, this becomes a signature generator of complex hidden sector phenomena. So my favorite signal generator for complicated cosmologies and astrophysics is neutral naturalness. Let me explain that very briefly. Neutral naturalness solves the little hierarchy problem. I'm probably not going to go into this level of detail, so let me just say it in words. So the point is that in the standard model, the Higgs boson couples strongly to particles like the top quark. And quantum field theoretically, this makes the Higgs boson unstable with relation to, in relation to unknown quantum mechanical effects at very, very high scales, like the Planck scale. Yeah? Now, you can remove that UV sensitivity by either introducing new symmetries, which cancel those quantum corrections, or by making the Higgs boson not a fundamental particle, like the proton is not a fundamental particle. In that case, its deep UV characteristics have no meaning. Yeah? What is a proton at a TeV? It doesn't matter. Yeah? So there are various standard solutions that do this, like supersymmetry or composite theories. Neutral naturalness is a different class of theories that uses a discrete symmetry. It essentially copies the standard model into a mirror sector. So now we're getting somewhere. And this mirror sector is very similar to the standard model. And this mirror symmetry is what protects the Higgs mass at low scales. So let me stop there. And if anyone has more detailed questions, I'm happy to go into that. The point is you are solving the hierarchy problem by introducing a copy of the standard model, an exact copy, except that if it was an exact copy, then the Higgs boson that we observe would actually be an exact mixture between the two Higgs bosons. Because the Higgs boson is at the center of the story, and it would be perfectly mixed between the two sectors. But we observe the Higgs boson at the LHC, and it's sort of standard model-like at the sort of 70% level. So not at the 100% level, because we don't have that precision, but at the 70% level. So that means in order to alleviate this, the light degree of freedom that we call the Higgs has to be, you know, more than half standard model-like. It's a quantum mechanical superposition that's like 70% standard model as opposed to 50-50. And you do this by raising the vacuum expectation value of the Higgs in this sector compared to here. So that means that all your quarks and leptons and everything else and the W and Z bosons are heavier by a factor of 3 to 5. And this ratio is just the ratio of VEVs, the B sector of VEV versus the A sector of VEV. So it's slightly uplifted. Yeah? Not that much, but somewhat. So that's fine, but now you have a mirror sector which has also mirror photons and mirror neutrinos. And no matter what you say about the relic abundance or about, well, the relic abundance is 0, the thermally, this is like a standard model, so it annihilates away. But photons and neutrinos are going to be around, so they're going to give you delta N effective of about 5. So that's very much excluded. So the minimal model is very elegant, but incompatible with established cosmology, okay? So CMB measurements. So how do you fix this? Particle theorists can enter the model and go, oh, let me just rip out all those degrees of freedom. And that's fine, actually, in sort of in a model building sense, because not all parts of this model are required to solve the hierarchy problem. And if you do this, then you essentially, this is a signature space of a light particle mass that arises in this model and the top partner mass. The point is you can probe that at colliders, and that's that other leg that I was talking about. How if you have the hidden sector that's not stable, you have collider signatures, you can probe that very well. But I want to talk about the cosmological solution, which is essentially a mechanism of asymmetric reheating. So what's the problem? The problem is I have a mirror sector. I'm not even saying anything about whether it contributes to dark matter, but it certainly contains photons and neutrinos. And this mirror sector is talking to us via a Higgs-like coupling, which freezes out at about 3 to 5 GeV of temperature. Yeah? So that means that not that much happens below that, so they're at roughly the same temperature, and that's why delta N effective is 5. You're just counting photons and neutrinos. But if you could heat up the standard model sector relative to the mirror sector, yeah, that temperature difference would mean that delta N effective is scaled down, yeah, just because the mirror sector is now colder. And that's what the asymmetrically reheated mirror twin Higgs does. So let me introduce this model. We're essentially taking a solution to the hierarchy problem, this mirror twin Higgs model, and now we're saying, hey, what if we had a particle that decayed out of equilibrium after the two sectors had already thermally decoupled? If that particle had an asymmetric decay that favored the standard model, then it would dump more entropy into the standard model sector than the mirror sector. And the standard model sector would cool more slowly and effectively would be heated up relative to the mirror sector. And that would solve the cosmological problem of the too much delta N effective. Yeah? So that's what you can do, and it arises very naturally by solving the neutrino mass problem. So neutrinos have a mass. We have to add those mass terms. In the mirror twin Higgs, when you do that, you very naturally get a right-handed neutrino that has a lowest mass eigenstate that is an even admixture of the mirror sector neutrino, right-handed neutrino, and our sector right-handed neutrino. And what this right-handed neutrino does is it decays out of time. So it's a long-lived particle. It decays after the universe has cooled below 3 or 5 GeV, but before BBN. And this decay width scales as the right-handed neutrino mass squared, as the standard model neutrino mass squared, divided by the W boson mass to the 4th. And that just comes from drawing the Feynman diagram. But what this means is that the ratio of the decay into the standard model sector versus all of its decays is controlled by the ratio of the Higgs VEVs, because both of these masses are controlled by the same Higgs VEV in each sector. What this means is that this right-handed neutrino that is fairly long-lived and forces the universe to enter a brief period of matter domination below 5 GeV, yeah, it decays most of the standard model by an amount that is given exactly by this ratio of Higgs VEVs. And this delta N effective roughly gets scaled down by the same ratio of Higgs VEVs squared. So what was previously 5 is now something like 0.5, which is a bit more reasonable. Yeah? So the characteristic scale of this is sort of a few squared. Yeah? So this could be 10. Yeah? And you can make this more realistic, but it's the same story. So let's boil this particle physics down to sort of the minimal cosmological phenomenological story. This particular model, the dilution is dictated by this Higgs VEV ratio. And in this particular model, this Higgs VEV ratio via the dilution sets delta N effective. Yeah? The more I dilute the model, the colder the mirror sector gets, the smaller delta N effective that I measure in the CMB becomes. In this model, which I think is very nice and natural, this exact same parameter sets a Higgs observable at the LHC, the amount of invisible Higgs decays. And so what you could do is you could measure this invisible branching ratio, which right now is unknown at the 30% level. In the future would get constrained at the 1% level. So this model would predict a non-zero definitive signal at the LHC from this observable which would tell you what this number is, which would tell you what you'd expect to see in the CMB. However, that is much more specific than the general asymmetric reheating mechanism. You could imagine different kinds of unstable particles that don't follow exactly this relationship. So in this particular model, this parameter, which controls the masses of the fundamental particles in the mirror sector, is measured by the Large Hadron Collider. In this particular model, this and this is related, but generally we can leave this as a free parameter. The amount of dilution is something that you could model build. Yeah? And finally, this already tells you a lot about the cosmology, but also if you have any kind of relic density, if you have any kind of asymmetric relic in this mirror sector that would constitute a form of stable dark matter, that will obviously also be important. Yeah? So again, we're being agnostic, and we're saying, I'm going to say that some fraction of dark matter is these mirror sector particles, mirror protons, mirror electrons, mirror neutrons, like literally these kinds of copies. Yeah? And these three parameters will define for me a rich family of hidden sectors that are motivated by the hierarchy problem. And now I can ask, what does the cosmology and astrophysics look like? The question is, how cold is the mirror sector? In other words, what's delta N effective in the CMB? Hopefully less than 0.6. What's the Higgs VEV in the mirror sector? It's going to be, in order to be a natural theory that solves the hierarchy problem, 3 to 6 times. 3 to 6. That's a number that I can measure at the colliders, and it controls the masses. So the mirror electron is this many times heavier than our electron. Yeah? Not quite for the mirror proton, though. And how much of it is left once everything annihilates away? Yeah? The mirror baryon asymmetry. So what does it do? We have to, yeah?
So just to recap quickly, so these are completely independent?
We treat them as independent. In the particular model that we like most, these are connected, but really they should be seen as independent because we want to probe a particular mechanism of having this kind of mirror sector that's diluted in some way, and then what does it do? Yeah, exactly. So for now, think of them as independent. But they have sort of reasonable numbers, like point few, a few %.
In principle, there's then all the mirror matter would form mirror stars and so on, right?
So we're going to recalculate all the things. That's right. So
saying that because we have constraints on additional objects.
yeah, absolutely. So that's right. So, so generally, yeah, we'll get there. Yeah. Please interrupt me.
The bigger concern is that it would dissipate, but there's really a copy of the standard model, and we know it doesn't.
Right. Yeah, sure. Yeah, we'll get there. We'll get there. We'll get there. This talk is way too long, so I'll sort of fly through things, and then you guys can interrogate me. But let's just start at the beginning of where we have any kind of empirical handle, Big Bang nucleosynthesis. So the only difference to the standard model at this point is the different quark masses, which are dictated by this Higgs VEV ratio. The quark masses will change the proton masses because of the running of the strong coupling constant. So this is something that I can compute. The proton-neutron mass difference depends on the fundamental quark masses in a certain way that I can determine from lattice simulations. I know what these masses are. The upshot is that as a function of this ratio of Higgs VEVs, few, the proton is like 20 to 40% heavier than our proton. The proton-neutron mass difference is sort of a few to 10 times more than in the standard model. So now we can start doing some basic nuclear physics. If we want to start doing nuclear physics, we need to know about deuterons. BBN relies on the deuteron bottleneck. We're not going to be doing anything past helium. Yeah. Obviously, BBN in detail is hydrogen, helium, lithium, beryllium, boron, all that business. We will just say, what's the helium fraction? That's a 0th order question. Yeah? And for that, we need to know the deuteron binding energy. Luckily, in the last few years, people have done lattice simulations with different pion masses, which is essentially the same thing as doing lattice simulations with different quark masses. And we can rejigger those results to get estimates. And again, we're being very coarse. We're just kind of including all the lattice simulations, estimates of the deuteron binding energy. And it turns out that these very generous uncertainties are not going to actually affect our result all that much. Similarly, we can get the pion mass. Yeah? So now we can see that in this mirror universe, the neutron, because we know the neutron proton mass difference, the neutron is stable inside the deuteron. This is binding energy. Blue is the range of deuteron binding energies in the mirror sector. If the binding energy is above this green dotted line, then the neutron doesn't want to decay if it's inside of a deuteron. So luckily, we have deuterons and we have helium. Everything is nice and stable. That's super interesting because the deuteron is very, very accidentally stable in the standard model. And that accident seems to persist at heavy quark masses, which is keeping lattice physicists very busy. They're super excited about this. So we stumbled across this and kind of used their results, but they're super super chuffed that if you kind of warp nuclear physics, these things that seem to be cancellations with the nuclear effective theory are actually robust, which we don't understand. So that's fun. But here is a cosmology BSM, beyond standard model application. So how does BBN in the standard model work? I think many of you will know this much better than I do. Essentially, you compute the neutron-proton weak conversion freeze-out ratio of about, at a temperature of about 0.2 MeV, and it ends up being like 0.15. And then you know that the deuterium bottleneck means that helium doesn't form until the deuteron is stable enough to sort of catalyze this fusion reaction. So the temperature has to drop to 0.1 MeV. That corresponds to 180 seconds, and that's not that much less than the neutron lifetime. So you have to scale down the neutron abundance by this amount that decays. And it gives you about 0.12, which gives you the familiar 24% helium fraction. So that's your sort of first order BBN. Okay? We can do this in the mirror sector. The temperature is going to be scaled down by an amount dictated by delta N effective. The neutron-proton conversion cross-section is depending only on the neutron-proton lifetime, neutron-proton mass difference, and the W mass, so you can compute that. You get a prediction for the freeze-out ratio of neutrons to protons in the mirror sector. And let me say this. Assuming the ratio of the mirror temperature to the mirror deuteron binding energy is the same when the mirror deuteron bottleneck resolves, the neutron decay only reduces the freeze-out abundance by 10%. What that means, in simple words, is that the neutron is shorter-lived in this model, but it is less short-lived and the deuteron is more stable. The deuteron becomes more stable in this model. The neutron becomes quicker to decay, but less quick than the deuteron is more stable. So in other words, this part of the story you can ignore. Yeah? Which is why these big error bars didn't matter. The deuteron, even here, the deuteron is stable enough, neutron decay did not matter. And you have a very interesting prediction, 75% mirror helium. So this stuff exists, if it exists, and roughly independent of how much there is. Like, as long as this stuff is kind of thermal, my mirror sector, however much of it there is in terms of the dark matter fraction, is 75% mirror helium, roughly 25% mirror hydrogen. Okay? That's quite robust. So now what? Let's start looking at the possible effects on large-scale structure. And I'm stealing my collaborator Yushin's slides. You guys know this much better than I do. So here is the matter power spectrum. I believe red is measured by the CMB and evolved forwards, assuming lambda CDM, to kind of coincide with these large-scale structure measurements. This is small. This is big. We analyze this in the sort of linear regime, sort of that way of this line-ish, by kind of decomposing into Fourier modes and just evolving linearly using linear gravity. So the way that this, keep in mind, what are we doing here? We have a sort of 1 or 10% dark matter fraction that is these mirror baryons. Yeah? They have their mirror, it's mostly mirror helium and a quarter mirror hydrogen. It's fully ionized, and then it stops being ionized after a while once it cools down enough. Interestingly, this sector is cooler than we are, but it has a higher binding energy. So it has a higher binding energy, so it wants to recombine sooner, but then it's also colder, so that happens later. So what's going on, right? So you have to do it a bit carefully. And the deal here is that just like we have baryoacoustic oscillations, this is going to have twin baryoacoustic oscillations, yeah, with kind of different masses and different ionization thresholds, but the same kind of physics, which means that dark matter structure growth on smaller scales that enter the horizon prior to twin recombination is suppressed. Yeah? So this will affect structure growth both by suppressing dark matter structure because a certain fraction of dark matter now doesn't grow until it's recombining. And this oscillation pattern will leave its imprint on the large-scale structure power spectrum. Okay. So, yeah.
Sorry, I'm just a little confused. So you're talking about you have the standard model baryons.
That's right.
Your baryons. So what's this? Is the CDMS separate?
Good. Sorry. I should have mentioned this before. We're agnostic about what the rest of dark matter is. Yeah. So my grad student Shane is working on a model that tries to make that more explicit, but there are many things that you could do. So essentially, we say we have some fraction of dark matter be these interesting mirror baryons, and then the rest is cold dark matter. It could be something more interesting, but for now, we just said let's start easy, and that turns out to be very sort of simple to do in the models. Yeah. So we have CDM, whatever, 90%, and then 10% mirror baryons or something like that. Yeah. So we need to know when these things recombine. So we did the full calculation for hydrogen. just essentially the recombination calculation, stuff that you guys have done for the standard model. For helium, we kind of took a shortcut using Sayer's equations. The thing that we're really after is at roughly what times do these mirror baryon components recombine. And it turns out that compared to the standard model, they recombine sooner, which makes sense because the ionization energies are higher by that VEV ratio of 3 to 5. So at a 3 to 5 times higher temperature, they want to condense. Now the temperature itself is lower, but it sort of works out that you end up recombining a little bit sooner. So being particle physicists, we are scared of class and other mighty softwares and Markov Monte Carlo change and all that business. So we sort of, we did something that was a little bit simpler. What we did is, let's just take let me see if this effect is even in principle observable. Let me take a sort of benchmark cosmology where I add a certain amount of dark radiation just to get the delta N effective to be whatever my input parameter is, because we know that delta N effective isn't observable, but that's kind of not the one that we're after here, right? So let's take lambda CDM with a little bit of dark radiation just to get delta N effective to be the same value, 0.5 or whatever we use, and compare that to the mirror twin Higgs model with the same amount of delta N effective to get what is the extra signature on top of delta N effective that you get from large scale structure from CMB measurements, yeah? As far as the power spectrum is concerned. We take the ratio of the power spectra at a scale k of these two models, just evolved forward. We're not doing any kind of big fit or whatever, but if this number is, noticeably different than 1, then there is a reasonable chance that once you do the full analysis, this should be discernible using measurements of the matter power spectrum.
So you're basically trying to say, if I know that there will be a degeneracy with an effective anyway, is there
That's right. That's right, exactly. So we're not doing the full fit, but just to show, yeah.
So what about gravity?
Gravity.
So
Well, I mean,
these twin particles and these normal particles, and
Oh,
they all interact. They're together. They're setting the gravitational potentials.
yeah,
So
absolutely.
you're evolving the system
Together. So we have baryons, twin baryons, and cold dark matter in one, and gravity.
Okay, but the gravitational potential wells are determined by the total.
That's right. That's right.
And, okay.
That's right. Absolutely.
And you have adiabatic. So the initial conditions are. It doesn't matter. Does it matter if they're in phase with the normal particles or not?
I mean, the standard model stuff is kind of, what do we do for initial conditions? I think the same as the standard model.
Okay.
Just cooled down. Yeah. Yeah. I think that's probably a conservative assumption. Yeah. Okay. So what happens? We get a suppression of the power spectrum at sort of smaller scales, which you would expect, compared to the non-twin baryon scenario. Yeah. So at smaller scales, you have this oscillation pattern, but that's in the nonlinear regime, so who knows how to trust that. But even in this sort of sigma 8 regime or a little bit above it, there are sort of, what did I choose here? Delta N effective of 0.4, reasonable ratios of sort of 3 for this VEV ratio. I get order 5% deviations in the power spectrum at certain regimes where I'm still in the well-controlled linear regime.
So if I wanted to make all my dark matter from mirror.
Oh, I can't do that. Oh, I can't do that. Sorry, this is a few percent. This is for a total of 7% of dark matter being mirror baryons. So to answer the other question, we're not going to have this be all of dark matter. So this is not sort of late 90s mirror dark matter. This is sort of a few percent where things like bullet cluster and so forth are okay. Yeah, but even at a few percent level, this will show up. Yeah, so this is very detectable. Good. This is how it's sound horizon, but I'm not sure if you could see this in the nonlinear regime. And where things stop being the same, that measures the temperature of mirror recombination. Okay. So obviously, lots of cool measurements are coming up. CMB stage 4. Let me show this one first. Essentially, again, we can't say, oh, for sure, this experiment will see it to this precision. But CMB stage 4 will see these kinds of deviations at the percent level. Yeah. And so here's our power spectrum ratio. Let's see, power spectrum ratio as a function of R all and as a function of VB over VA. So if I can measure the power spectrum ratio at the, say, 5% level, yeah, then I can constrain the model to lie below this line. So regardless, and this doesn't really depend that much on the Higgs VEV, it really just measures the mirror twin baryon abundance as a function of dark matter. So for sure, it seems that CMB stage 4 will be able to determine this, will be able to detect this at the percent level. So right now, Lyman alpha constraints tell you it could be 10%, and that's broadly okay with bullet cluster, et cetera. But future measurements would detect this at the 1% level. Fine, good. Let me not go there. Okay. So we have pretty well established large-scale structure signals. What about the CMB itself? So I already talked about this a little bit in the. I already talked about this because delta ineffective was like one of the input parameters for our model. So clearly, a non-zero delta ineffective is an important parameter. And by the way, it would be, I think, a little bit difficult to make that go to 0. So you really expect point few. Okay. What is a smoking gun, though? And of course, in a particular model, you might relate this delta ineffective to the LHC observable of an invisible Higgs decay, but that's model dependent. What I think is the smoking gun is that because this is a standard model copy, as far as the photons and neutrinos are concerned, they really are standard model-like in their relative numbers of degrees of freedom. So future experiments will be able to distinguish free streaming versus scattering delta ineffective. Yeah? So interacting dark radiation versus free streaming dark radiation. And that ratio is going to be standard model-like. Yeah? Now, it's not exactly 3 over 4.4 because there's an extra little piece that comes in before it enters the CMB that we didn't understand. But the point is that it's the same as the standard model. Yeah? So no matter what it is, it's the same as the standard model, right? So that's just a very tight prediction of this model. So if we find this, then that's very suggestive. Yeah? Cool. So now we sort of have the big picture. How am I doing for time? Oof. So now we have the big cosmological picture sort of figured out, at least at the sort of order 1 level. So let's zoom in and see what happens with these mirror baryons as part of our dark matter halo. And this is important because we want to know where the mirror baryons are today, because it would be cool if we could detect them in dark matter dark detection experiments. And it would be even cooler if they give rise to novel astrophysical phenomena. And they do. So at this point, we proceeded. We just had lunch today, and this was my fortune cookie. It says, if you think you can, you can. So this is the particle theorist mantra. We're like, haha, baryon distribution of the Milky Way, no problem. We got this. We do not got this. So this ended up being a 50-page paper of which 30 pages are just nothing but crying onto the page and telling other particle physicists to never try and do anything like this, because feedback is impossible, as you guys know. Yeah? So I have a bunch of slides in the backup, but to essentially sum it up, if there was no nuclear physics in our mirror sector, we could actually try and do things that would be somewhat reasonable, right? You could have dissipation, you could have disk collapse, there'd be no real feedback. It's sort of doable-ish. But because our mirror sector has nuclear physics, we've established. I mean, you get stars, you get mirror stars, you get everything. So that's the thing. You get everything. But it's like the nuclear physics is like, and the chemistry is order 1 different from the standard model, which means that you can kind of track it at the micro level. But what kind of star do you get out of that? Well, OK, Jack's working on that. But how do you go from what kind of star you have to what the feedback number is you plug into your simulation? I think even for the standard model, you don't know that yet. You're sort of, there's no. So I spoke a lot. I took advantage of you guys being here and spoke to Tom Quinn and Norm and other people, and essentially just trying to understand this whole feedback story. How much does it matter? How robust is it? And my understanding from talking to those folks is that essentially we are not even yet close to going from first principles astrophysics to a number that you put into your magnetohydrodynamic n-body simulation, right? Like maybe in the future we'll reach that point where the resolutions become so tight that you can predict the feedback number, but not yet, if I understand correctly. So now twiddle the nuclear physics, twiddle the stellar astrophysics. How do you get the feedback number? Who bloody knows? Yeah? Sure, maybe. I don't know. No. Yeah, I mean, you'd get something. You'd get something. But the point is, we just have no idea. Like, for sure there's a limit. Here's the thing. For sure there's a limit of the theory where I dial the Higgs wave to be the same, where everything is in fact the same, and for sure I have supernova, and for sure I don't know what I'm doing. Okay? That's right. So let me dial it to standard model, and then I don't know what I'm doing. And then now let me dial it away from standard model. The stars become weirder and they glow in X-rays. And
are you suggesting that LIGO has been seeing emergence of black holes formed from mirror stars?
I will neither confirm nor deny those accusations. Now, there is actually, I mean, there is interesting, I mean, oh, you're referring to the 20 black hole mass, the 20 solar mass thing. Maybe. I'm going to go on record saying maybe. But that is actually a cool point. The point is, this is a sort of generator of weirdo astrophysics that wouldn't show up with normal observations, but it would show up with some others. Yeah. Anyway, the point is, we end up going through a whole rigmarole and calculate what we can, and we do learn certain qualitative things. We learn that the cooling timescales go as 1 over how much there is. We know that the cooling is on average less effective than in the standard model, so the collapse is less fast. The disk is maybe smaller, but maybe it's also not a disk at all because you have no idea what feedback is. If there's really tiny amounts of it, then it probably doesn't cool and it just stays at a puffy halo. But these are qualitative and they're sort of helpful. Like there is help that is valuable, but at 0, we just have no idea what the distribution is. So we cut our losses. So we did this for 30 pages, and then we cut our losses and we say, okay, we will just consider 2 edge cases for the purpose of dark matter dark detection. We'll consider a couple of edge cases that seem reasonable and should bracket what the phenomena actually are. The first edge case is that the local mirror baryon distribution is halo-like. So in other words, locally speaking, we are in a sort of puffy, almost CDM-like halo, or where there's a very small disk and we're on the outskirts of this halo where like various radiation pressures and whatever maintain a sort of roughly halo-like distribution. This could be due to slow cooling, due to very strong feedback. This could be if you have a small disk, but you keep the various conveyor belts that are active, keep some of these halos suspended, which if I'm not mistaken is actually the case in the standard model. There's a lot of stuff outside of our disk. So in that case, so that's kind of one qualitative scenario. The other qualitative scenario is that the local mirror baryon distribution could be disk-like. In other words, we're inside of it. And in that case, so the 2 different scenarios that we're looking at is that if it's halo-like, just to have a sort of outer edge, this is going to be, generally speaking, the optimistic scenario for dark matter detection because stuff moves faster, right? Unless a mirror star flies through the Earth. But like the sort of mirror interstellar medium, right, is going to be faster in this case, just gravitationally speaking, than if it's settling inside of a mirror disk. Now, of course, all this could be locally variable. Like our interstellar medium is sometimes ionized, sometimes not, sometimes hot, sometimes cold. But just to have bracketing cases, we assume it's CDM-like in terms of its temperature, in terms of its sort of temperature distribution, which actually is roughly what you'd get by hydrostatic equilibrium. But again, this is just an edge case. Yeah? And we are considering fully atomic or fully ionized, although if it's in this case, I don't really see how it could be atomic. It would probably be ionized. And here we just say, even if it's 1%?
Yeah.
How so?
Because you form a mirror star or a star binary probably, and we looked at enough ordinary stars to know that there isn't any dark.
So it's not clear to me that if the galaxy formation is totally separate, like these are non-interacting sectors, they don't talk to each other.
You have dense clumps of molecular gas forming.
Sure, but the different sectors cool at different rates. They have different Jeans lengths. They have different feedback rates. They have different cooling rates. I would be thrilled if you work out the constraints.
No.
Good. So for this edge case, I mean, if this is excluded, that's fine with me, because we're assuming pessimistically that the only velocity that this stuff has relative to us is the Earth going around the sun and the local stellar velocity dispersion, just to have a sort of lowish relative velocity that we can try. And essentially, these are just edge cases that we use for direct detection. Okay? And these are going to give us error bars. So with that in mind, let's do direct detection, and we will consider various local helium fractions and various local ionizations. Okay? So being very agnostic. So now we can look at mirror baryon dark matter dark detection. And how would I detect these? So there are 2 couplings that I can use. The first one is the Higgs portal. That is the fact that this low-lying Higgs that I've detected at the LHC would be a little bit talking into that sector. It would poke its nose in. But that coupling is just way too weak because the Higgs couples to particles proportionally to its mass, roughly speaking, and it's just not enough to give us any kind of signal above the neutrino floor. The photon portal is interesting. It corresponds to, in the Lagrangian of the standard model plus the mirror sector, you write down a non-canonical photon mixing term. If there are any of my QofT students in the audience, this was the solution. It's actually roughly true. But anyway, the exam was due during this talk, so I'm going to go home and find so they were allowed to come to this talk after they hand in their exam. The point is that there is no symmetry that forbids this term, and naturally it is of order sort of a few loops, a few quantum mechanical loops, which gives you an estimate of being small in 10 to the minus 9. This is a mixing between the dark photon and iron photon, kind of like a neutrino oscillation, but different. The point is, this is great because we don't want this to be bigger than this, because if it is bigger than this, it will re-equilibrate the two sectors after the asymmetric reheating. So the whole point, cast your mind back, the whole point of this rigmarole was to fix the minimal twin Higgs cosmology. And we did this by pumping energy into the standard model sector. It would really be bad if this portal, this coupling, would put the energy back into the mirror sector after that. So it works out really nicely that the sort of natural maximum size of this coupling in the model is approximately the maximum size it's allowed to be without ruining this cosmological mechanism of asymmetric reheating. So that's kind of neat. So we need to detect nano-charged GeV scale dark matter. So we can look with nuclear recoil detectors like Super CDMS here at Snow Lab, here meaning within this country. Fairly standard story, familiar to you guys. This is super nice because they have much lower recoil energies than any other nuclear recoil detector. So if you're detecting GeV scale stuff, your detector is not made of helium. It's made of something much heavier. You need really, really tiny recoil thresholds. Yeah, so this guy can do it. More recent and very exciting is the possibility of dark matter dark detection via electron recoil, where you are literally knocking an electron out of some shell and detecting it. And the sort of most promising, so there's some existing stuff in xenon, but they have a very high threshold. The most promising of these is Sensei, a silicon detector, which is essentially a huge astronomical camera with really crappy resolution, but really, really fat CCD elements to give you a bigger target mass. And those things are so sensitive, thank you astrophysicists, that they can detect 2 electrons being liberated in each paddle. And that turns out to give you an electron recoil detector with a threshold of 4.7 eV of momentum transfer, which is minuscule. So what this gives you, if I were to pretend for a second that this was cold dark matter with just a single species that has this portal, here is the super CDMS sensitivity. So at a GeV, you can probe millicharges at the order of 10 to the minus 11. The Sensei experiment is sort of similar at higher masses, but goes down to, it can detect light dark matter at the electron mass scale with 10 to the minus 13 millicharge, really impressive. You can also imagine things like superconductors. That's a little bit more fanciful, but that could be important. Essentially, there are no meaningful constraints right now on these mirror baryons, but for the future, Super CDMS is already taking data, and Sensei has already received funding. So in the case where you have an ionized halo of mirror baryons with different amounts of helium, it doesn't really matter. The important thing is that this is a 2-component dark matter system that's in thermal equilibrium, which means the mirror electrons are much, 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 much faster than the mirror protons, right? You have some V0, 200 kilometers a second, but that is shared according to the square root of the mass ratio with the various constituents. So the electron is 60 times faster than the protons, the mirror protons. So the electron signal at Sensei is unbelievably sensitive. It could probe charges as low as 10 to the minus 14. Whereas 10 to the minus 11, 10 to the minus 10 is where the nuclei show up, the mirror nuclei hitting the Super CDMS or Sensei detector. If you have a mirror disk, all the velocities are smaller. And I mean, this should be taken as qualitative because, again, we don't know, the real truth is in between these two, depending on how these things arrange themselves, right? But the mirror disk, everything is slower, which means the mirror nuclei just don't show up in threshold experiments anymore. They move at 20 kilometers a second, who cares, okay? The mirror electrons still move at about 200 kilometers a second. So now they're sort of CDM-like, and you get these 10 to the minus 11, 10 to the minus 12 sensitivities. So even in the disk scenario, as long as there's some mirror electrons, as long as there's some local ionization fraction, you could in fact see it. If everything is atomic, then you're out of luck in the disk case. And then and essentially, depending on how you correlate various electron versus nuclear recoil experiments, you can actually diagnose the local state of ionization and the local helium fraction. The local helium fraction would show up in the nuclear recoil spectrum, depending on, yeah? So that's direct detection. I believe I have 5 minutes left to talk very briefly about mirror stars. I think many of you have already heard this at the PI CITA seminar like 2 weeks ago. This has been a super fun project. It's also been one where you know, I'm not a stellar astrophysicist, and my postdoc Jack is extremely excellent, and he's becoming one, but not yet. So we have been kind of oscillating between, oh, it's optically loud. Oh, it's X-ray loud. Oh, shit, things scatter. It's optically loud. So we're going in between. What is staying fixed is that the amount of power output of these things is observable. So this is extremely preliminary, and we are confident that we are converging towards what the actual signature is. So let me tell you this, but please be kind because the particular plots themselves are already out of date, okay? And I'm going to go through this very quickly because I'm close out of time. But we've now moved on to this last question, which is, could these mirror baryons that are around us give rise to novel astrophysical phenomena? And now we can sort of take a turn and think more generally about mirror stars. Because what we have here is that we have a hierarchy problem solution, motivation for mirror stars, which is really nice because a perfect standard model copy of dark matter, mirror dark matter, is an old idea. Robert Foote and friends have been dreaming about this since the 90s. But that was in a somewhat specialized cosmological context. And I don't think it ever caught on. But even those guys that were really caring about mirror dark matter, they never really studied mirror star signatures. And I think we have a much more interesting reason to look at them. We have a UV. This is coming back to hidden sectors. This is coming back to using fundamental mysteries as signature generators for explicit hidden sectors that generate astrophysical phenomena. The hierarchy problem gives me this mirror sector that's standard model-like, but has this adjusted Higgs vev. So the physics is standard model similar, but still super different in all the ways that matter. Even that little bit of difference is already almost too much to handle. This family of hidden sectors is similar but different enough to give us very different detailed stellar astrophysics. So before we even get into, you know, there's a very natural question, what kind of stars do you get? Well, let's figure out how we would see them first. So we're going to factorize the question. Number one, if I have any kind of mirror star that talks to us via a photon mixing, or from a dark matter sector that talks to us via photon mixing, I'll cut this short, I'm not going to go much longer. What do they even look like in the sky? Nobody knows yet, but it's answerable. The second one is, given a certain hidden sector model, what are the characteristics of this mirror star? Yeah? Does it live for 10,000 years or 10 trillion years? Is it this big or bigger than the sun? Yeah? It could be this big if the mirror sector is weird enough. Yeah? So this is fun. This is like stellar nuclear physics, like alternative universe fan fiction. Like everything is different, but you can sort of figure it out. Okay? So we are started thinking about this, figure out first for a general mirror star what the signature looks like, and Naturalness is a great signature generator. So the next paper is going to be figuring out these stars. So I'm not going to go through this in detail, which is just as well because the details themselves are converging but still in flux. The main source of signal that I just want to qualitatively leave you with is that if you have some mirror star, it's going to radiate in dark photons. And certainly some amount of surface signal will actually convert into our photons, but that is very hard to see. What's actually going to give you signal is that this mirror star is going to fly through, and by the way, sorry, in all of this, you know, I'm assuming that there's this mirror photon mixing, yeah, which is a motivated thing that by symmetry should always be there at some level, yeah, some small level. The key is that this mirror star, if it's observable and it's a very faint signal, it's going to be close-ish to us. So it's going to be flying through our interstellar medium, and it's going to, just like a windshield, it's going to be accumulating bugs on the windshield. So standard model stuff on the interstellar medium accumulates in this sort of tight standard model nugget that kind of scatters a bit and goes down and down and ends up being a tiny, tiny amount of matter.
Our sun doesn't accumulate matter from the ISM.
Sorry?
Our sun doesn't accumulate matter from the ISM.
It most certainly doesn't because, well, I mean, the ISM and the sun are in the same particle physics sectors. So the sun pushes things out with radiation pressure, et cetera. This is a star that has its own nuclear physics, its own photons. It shines in its own photons. It's this ghostly dark matter clump, really.
So why don't they go through?
Because there is a tiny interaction
Similarly, we should then have some mirror matter.
Yeah, there is. So yeah, our sun will have a bit of mirror matter in its core, and this star will have a little bit of standard model matter in its core. So this part is a standard asymmetric dark matter story, where you have a small cross-section, and at the end of the day, the star is still pretty big, so a tiny interaction cross-section will still cause some of the stuff that flies through it to accumulate. The cool thing is that once you have some amount of stuff in the middle, you now have a catalyst to turn these photons into our photons via mirror-Thomson scattering. So an electron, a standard model electron, will talk to a dark photon, it'll absorb it and emit it as a normal photon. So it's converting it, and you get an X-ray signal that tells you that is essentially X-rays from the center of the mirror star. Yeah? Imagine if our sun was transparent. The core would be the brightest thing there is. That's what this is, obviously much, much fainter.
No, but X-rays can't get through the sun.
No, but these guys can't. That's the point. They've been converted. This guy can't get through the sun. Mirror dark photons. So this is a mirror sun. It's emitting our X-rays because it captured a couple of electrons or protons. They got eaten up and then with this tiny, tiny coupling, right? And emitted as normal photons that don't talk to this guy. So you get a thermal X-ray signal straight from the core of this thing, which is so cool. Come on, it is, right? It is so cool, yeah? Thank you. And also, because this standard model nugget has some thermal equilibrium that you can figure out, it has typically like, it's way hotter than it has any reason to be. So it'll emit IR or optical or whatever, yeah? So the details at this point are still a little bit wrong. The point is, so the cool thing here is that you're going to have two sources of spectra. This is not correct in detail, but it's morally correct, okay? You have sort of two sources of signal. You have an X-ray spectrum that comes from the core via this conversion process, and you have a optical or IR spectrum that comes from this nugget being at a certain temperature and being continuously heated a little bit by the fact that it's in a little bit of thermal contact with this core of this mirror star. It's much colder than the core of the mirror star, but it has some temperature, like 10,000 Kelvin or something, yeah? So you have these two kinds of signals, and that's super distinctive. So we are slowly learning our way around an X-ray catalog, which is, boy, it's scary for particle theorists. So if you guys want to help us, please do let us know. But we started thinking about the signature in terms of a Hertzsprung-Russell diagram, where you essentially have a few different peaks in the spectrum, an X-ray peak and an optical peak that are both associated with a single stellar object. And just to see...
Binary, right?
Huh? No, it's not a binary. It's a single thing that has...
Almost everything that emits X-rays and optical is a binary.
Right, exactly, exactly. So this is not one of the Magnificent Seven. This is not some cataclysmic variable. This is not some binary, whatever. It's this crazy, you know, on the Hertzsprung-Russell diagram, it's all the way down here for the optical part and way over here for the X-ray part. And okay, again, the total power output is robust, but we have to still, we're working out some details here. The point is this is potentially observable in something like Rosat or E Rosita, and we might even already have it on tape as a weirdo object, but we just don't know yet exactly what the spectral shape is and exactly what the sensitivities of these instruments are. We're learning this as we go. If anyone wants to help, please let us know. The point is, here's the upshot of this. This is true. Mirror stars have a robust and highly distinctive signal. There's a superimposed X-ray spectrum. It's kind of quasi-thermal because it comes from different parts of the core and scatters a bit from the mirror star core with a optical thermal emission of the captured standard model matter. Now, the relative sizes of these we haven't yet figured out, but they're going to be both detectable if you look hard enough. The X-ray signal is probably going to be the first one that shows up. Upon detailed examination, this will look nothing like anything from standard model astrophysics. Yeah? Something that emits that amount of X-rays and is quite X-ray bright, has a little bit of optical. You could see it if you look long enough with an optical telescope, and it has a parallax, so you know how close it is. Yeah? You can't see it if it's too far away. And then if it's that close, you know exactly how faint it is. The answer is very. Yeah? So what the hell could it be? It's going to be something like a mirror star. So the next step is to understand if, well, the next step is to get the spectrum right. This is not quite right. But the next step is to understand if current sky surveys already have some sensitivity. So let me wrap up. Thank you for your patience. Hidden sectors in particle physics are motivated from sort of various particle physics perspectives, but they're incredibly awesome signature generators for really interesting, exotic astrophysics and cosmology that ties together telescope and X-ray observations of weird astrophysics objects with potential solutions to fundamental problems like the hierarchy problem. Thank you.
Let's say you had cosmic rays made out of mirror matter.
Yes.
At 10⁹ eV, presumably they act just as much as a regular. For example, if these things do generate cosmic rays, they might have a longer they have complete action and they might fill in the decay power.
I agree, although it does depend on the mirror magnetic environment, right? So what the mirror magnetic fields are, which we don't know, but I do agree that mirror cosmic rays would be cool. Do you want to write a paper? I agree. Like, the point is there's, like, once you take this fundamental thing as a signature generator, there's an infinite amount of things to check, and they're all kind of weird and awesome, quite frankly. So yes, mirror cosmic rays could be a thing. I haven't thought much about it, but yeah, maybe. I don't know. Maybe. I agree that they would probably scatter in our atmosphere, but in a really, really odd way, which is excellent. Yes.
Any more questions?
So you said that it's possible that they would be, these stars would be close enough to be observable.
Yes.
Is that consistent with the Michael-London constraints on the...
Good. Yeah. So is Harrison Winch here? No. He's an intrepid first-year astrograd who's looking into that for us. So in principle, that's exactly, it should be accessible. But so my feeling is that given the sort of reach of macho bounds, we're talking sort of percent level. So this is a super interesting question, but we're talking percent level dark matter abundance, and also these are not going to necessarily be distributed like dark matter. So when you do these macho bounds or whatever, you stare off into the Magellanic Cloud or whatever, and you kind of translate these macho bounds into abundance bounds based on some assumption about the distribution. But if these things are disk-like, then maybe there's nothing where you're staring and much more somewhere else. So it takes some work, but in principle, yes. But it takes some work, yeah.
More questions? I had a question. If you wanted to bet, would you say we'll be within range of seeing signatures from this first in colliders or in astrophysics?
You know, I have, oh God, come on.
So there's one that's being measured, right? You already said that.
So this guy will be measured, and we'll have a 1% scale measurement in 15 years, 10 years. So it's quite a long, and if that's the only thing there is, mildly boring endeavor, but very important. Yeah. So on 10-year timescales, we'll have this. If it's one of those non-cosmological models, we'll have all kinds of cool things within 10 years. And that's part of the reason why I'm building this Methuselah detector. Not me, no, my experimental friends. Now, whether we can see these mirror stars within 10 years, I mean, if they're real, the sensitivities are not that crazy. So maybe, but what I really like about this approach is that if you look at both of these angles, there's kind of no way to hide. So I think this kind of full coverage is one of them going to see something? I don't know, but I think it's completely plausible given how strong the motivation for these fundamental problems is, right? So the reason my thinking is influenced by the fact that in terms of the basic rules of quantum field theory, something like the hierarchy problem is to be taken seriously. In terms of the fact that we exist, baryogenesis is to be taken seriously, blah, 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 right? So these mysteries point you, in many cases, towards either loud collider signatures that we're now building detectors for, like these long-lived particles, or they're pointing you towards crazy cool astrophysics that you have to look for, maybe comb through catalogs, or maybe do a special search for, but in principle is accessible. So if you do both, I would be reasonably, I mean, I don't know, not pessimistic, not depressed about this particular thing. I mean.
Okay, so if there are no more questions, David's going to join us upstairs for a few minutes for snacks, so you can talk to him more, but otherwise,